calculate what's that answer going to be, not even going to have to say to a certain number of significant figures here. It's just what's the answer using significant figures. Well, we've got a 12 with how many decimal places? None. Which means our answer should have none, right? Because when we're adding or subtracting with decimals, you round down to the decimal places that is the least. So if that was 12.0, then we would have one decimal place, right? But because that's a 12, there's no decimals there, the answer should not have decimals. You're still going to add it and then round it, so we're going to end up with 16.7, which means we would round it to 17, right? If we add a really big number, like 2,000 plus 0004, here's something that you need to appreciate. The impact of significant figures, and why we care about significant figures, is because we're wanting to maintain a certain degree of accuracy. So, remember when we looked up the distance between the Earth and the Moon? Right? And we were given a number that had a lot of zeros on the end of it, a certain number of million miles. Well, let's say that I was asking you to add the distance between the Moon and the rock I just threw off of the surface of the Moon. Would that be a meaningful difference between those two numbers? Even if I could measure accurately how far I threw that rock, because that 0.0008 or that 0.0004, the fact that we can measure that small means I have a very accurate yardstick, right? But what's the, just think of it in terms of scale. Is that much of a difference going to matter if the number I'm adding it to is 2,000? No. So the fact that we lose all of those things when we add this for significant figures, adding 0.0004 to 2,000 is really not changing the number much, right? So that even if we can measure this a little bit really, really accurately, we did not measure that 2,000 really, really accurately. Unless, of course, it's 2,000.0000. That tells you we measured that 2,000 really accurately, right? So, significant figures, they're a sticky widget. You're, look it up. But mainly, it's just count the significant figures. When you're multiplying, your answer should be rounded to whatever the lowest one was, right? So if you had 2 sig figs, 3 sig figs, 4 sig figs, if you're multiplying, you round to the one with the lowest number of significant figures. If you're adding, then what matters is decimal places. So decimal places for addition and subtraction. It's whatever your smallest decimal is. And if one of those values has no decimals at all, if there's no 0.0, then your answer should not have decimals. But in every case, you're going to round to match the number of significant figures. So if it's 0.4, it becomes whatever that was. If it's 0.5 or up, it becomes one more than that, right? So that's where that 158.7 comes in. If it's round to 3 sig figs, what would it be if it was round to 2 sig figs? What would that answer be if it was 2 sig figs instead of 3? 160. Because then we'd be looking at 15 as the 2, and what's the third one that we don't want? 8, that rounds, so it's 16 or 160, right? I did have one person that answered some of their homework questions in scientific notation, and I was like, that's creative, but you had to know there's no way I was going to anticipate that one. So everybody got a lot of them wrong just because I was trying to guess. But there's there's a finite but large number of ways that you can answer these questions. So really the take-home lesson for me is don't do fill-in-the-blank questions, which I kind of already knew that. I was just trying to see how well it would work. So I might just have to invent some multiple choice or true false or turn the questions into something a bit more like that for future homework. And then this one, that last question on there where it talks about melting ice, right? It's a beautiful thing and I really liked it, but here's the way it works. You had a known, all right, before we even get there, let's talk about this. The reason why I drew this up here, these are equations that you guys don't recognize. I just made these up. The point of writing these two things is, because they are both equal to E, if we are talking about the same system, that means that I can put this equal to that. Because if 2 horses are equal to 1 goat, and 1 goat is equal to 2 chickens, That means that 2 horses are equal to 2 chickens. Did you follow that, or did I just confuse you? So, if we're putting this here, what I can do is I can take that E and draw out that same equation right here, and that is still true, right? Because this right here is true, that's what it was originally, and this right here is true, which means that whole thing is true, which means I can get rid of this thing in the middle and just do that, and then solve for, say, the change in time for whatever the heck those other variables are, if you have them all. Which in that problem, in that homework, you did. You had everything except for the amount of water that was in that container. So you could have done this if you really liked algebra. Or you could have done it without it. By simply conceptualizing the answer, breaking it into 2 parts. Because the important thing that was there, the part that may have been confusing, is it was asking you 2 questions. How much energy does it take to melt a known volume of ice? Right? And it was also asking another question, how much volume by weight, how much weight of water can you cool 8 degrees with this much energy? Those were the questions. The first one told you how much energy you had to work with. The melting of that ice, that told you how much energy you had to work with. That was the number you plugged in to the second equation to find out how much water that was enough energy to change by 8 degrees. And then, of course, you do the standard math of rounding to significant digits because there's a lot of multiplication and division there, right? So, I like that question, especially as a homework question, because it does force you, if you're going to figure it out, it forces you to go, I know this thing, and I know this thing. Can I take these 2 balls and actually see that they will stick to each other, they are related to each other? Because otherwise, you know a bunch of things, and it's just a whole bunch of balls that have no connection to anything else, and that can get really daunting. Having to remember just a whole bunch of random, disorganized, chaotic, and unrelated facts, that's crazy. But if you can organize those facts in your head, so that it's not 1,000 unorganized, unrelated facts, it's actually groups of facts that are related to each other, based on certain themes, then that makes individual little pockets of that a lot easier to grasp, and a lot easier to remember, and a lot easier to apply. Because otherwise chemistry is just a huge list of a lot of facts that don't have anything to do with each other, because you don't understand that they have everything to do with each other. So, that's that. I'm going to dive into chapter 6, because we really need to get that started. But, especially if we are actually kind of sort of keeping up with where we need to be, we can spend some more time talking about either the homework or the test. And then once class is over, I'll give you some pointers and remind you about some things about the test. Right? If we don't finish chapter 6, and by finish I mean, reasonably get to the end. If there's like 2 slides left, then I might just kind of be like, to finish those 2 slides. And then it'll be on the test that opens tomorrow. If there's still 30 slides left of this chapter by the time we quit for tonight, then it won't be on the test. Now, that doesn't mean that you won't have to worry about it. It just means that the test will be 48 questions over 3 chapters instead of 48 questions over 4 chapters. Which might be easier because there will be no questions about chapter 6. But it also means there's going to be a lot more questions about chapters 2, 3, and 4. And 2 and 3 were 80% math. So, now if that's math that you feel very confident you can do, then that might be in your interest. But what that does mean is that chapter 6 is guaranteed to be on the next test. So the next test might have 5 chapters on it, which means there'll be 50 questions, 10 from each chapter. Right? So you're not getting out of it. It's not like it's like there's not enough time to clean your room, so you don't have to clean your room. We're just going to do it next time. Right? So, let's talk about chapter 6. What are we trying to do? Chapter 6, ionic and molecular compounds. Let me go kill the light so we can actually see the screen, shall I? Fix that top. Thank you. So, here's a nifty thing that you may or may not know about most of the medications that you might give to someone. Most of the medications that you're going to be injecting, if it's in pill form, this will not be the case, but if it's in injectable form, well, actually even in pill form it might be. But certainly if it's in injectable form, it's going to be an ionic or like a salt, a version of an ionic compound that we use in order to create those medications. So, now it's probably not going to be part of the name, but as an understanding of chemistry, I would hope that you would be able to understand why it is these ionic compounds that we use in order to dissolve and store some of these drugs that we use. Alright, so ions. Transfer of electrons. The goal here for 6.1, and I should point out there's, I think, 9 sections of this chapter, which is why I'm going to try and move quickly. It's why we have, there's like 100 and, actually it's not showing it there anymore, 100 and some odd, 117 slides. It's a lot! So, an ion is where we're not sharing electrons. And this is a critically important thing. The whole chapter is not about ions per se, but the first section here is about ions. There are 2 ways to have, that's not true, there's more than 2. There are 2 primary ways to have really strong molecular interactions within the same molecule. One of them is covalent bonds, which we'll get to in a little bit, and the other one is ionic bonds. Both of them have everything to do with where the electrons are. Covalent bonds, you are sharing electrons, like 2 kids at kindergarten in the playground that have learned how to share, and they're sharing their toys with both of them playing with them. An ionic bond is more like one kid that's a little bit of a bully who steals the toy, and then the other kid is just kind of hanging around because he really, really wants it back. He's attracted to that toy, if you follow the metaphor. So in the case of ionic interactions, we are transferring electrons, but one of the atoms is going to be the one that owns that electron. It will be holding on to that electron solely, which will give it a negative charge. And the other guy, having lost an electron, or more than one in some cases, but in the case of sodium chloride here, the sodium loses 1 electron. Why? Because it's over in that first group, right? And so it has only 1 valence electron to lose before it's nice and stable. So it will lose an electron. Chlorine is over in our halogens, so it's going to gain 1 electron to be nice and stable. But when you have, in the case of sodium, 11 positive charges, and when we lose an electron, that gives us only 10 negative charges. So what is the charge of sodium? Positive 11 minus 10 gives you a sum of positive 1, right? So that's where our positive comes from. Chlorine has 17 protons with 17 electrons, but if it takes 1 from sodium, it now has 18. So 17 minus 18 gives you a charge of negative 1. And so that's where we have our positive and negative charges. And what happens to positive and negative charges if they are associated with each other? They do what? They are attracted to each other, right? Just like a magnet. Question?
So you're saying one atom will hold on to the electron of that specific element, and the other, I guess, atoms of a differing element will hold on? I mean, we'll try to take that electron.
We'll give up the electron.
We'll give up the electron.
One of them is donating its electron to the other one. And I don't want you to think that it's just like, here, you can hold this for me while we're hanging out. No. Chlorine is taking it.
And it's always a different element?
Yes.
Okay.
Well, yes.
Okay.
For our purposes in this class, yes. Especially for this chapter.
The one that takes is always the negative.
Correct. Well, assuming we're starting with neutral things to begin with. In the case of chlorine, yes, if we start with a naked sodium, a balanced sodium atom with 11 protons, 11 electrons, and we have a naked chlorine with 17 protons and 17 electrons, then yes, if that chlorine takes 1, it becomes negative. Now, the reason why I'm prefacing this is because later on when we talk about chemistry, biochemistry, and otherwise organic chemistry, we're going to have molecules that are starting out with a +2 charge. They're going to take an electron and it'll leave them with a +1 charge. So it's still positive, but it's not as positive as it used to be. So I don't want to say the one that takes an electron always become negative. But yes, if they start at neutral, yeah, you start at 0 and add a negative number, you're going to be negative. Right? So, now, could we have something that takes more than 1? Change this salt to something that I would not advise you ever actually ingest, to something where that second guy is taking more than one electron. Not so much from sodium, but just wants more than one electron. What could you do?
Hydrogen?
Hydrogen wants to give up, not gain. So we have, actually hydrogen wouldn't mind gaining, but then, other things happen. So if we take our chlorine over here, if we just move over to sulfur, sulfur wants to gain not one electron in order to be full, but two, right? So we could have an S2 minus, but then we would need how many sodium ions in order to balance it out? We'd need 2 sodium ions. So the salt for sodium sulfide would be disodium sulfide. It would be 2, actually that's not right either because we'll get a nomenclature later, but it'll be 2 sodium ions and 1 sulfur ion. But the sodiums will both be +1, and the sulfur would be -2. So, ionic compounds are compounds that are held together because of ionic interactions, which means that they only happen when you're drawing these things out if you're doing it completely and there are pluses and minuses involved. If there's no pluses and minuses involved, then it's not an ionic compound. Ionic compounds are things that stick together specifically and only because of the attraction between positive and negative charges. If you are holding on to electrons that you are actually sharing, and I'm going to use the word sharing in air quotes here between hydrogen and oxygen in water because oxygen never shares well, but it's still technically sharing its electrons with hydrogen, and so that is a covalent bond. That's not an ionic bond where one takes it and then they're attracted to each other because of the positive negative. It's because they're sharing it between them and they are now covalently bonded together. Both of these, ionic and covalent bonds, form relatively strong interactions between atoms. Covalent more so than ionic. So, what are the bonds that are holding this C3H8 molecule together? Are those covalent or ionic interactions? Do you see any positives or negatives anywhere on this label? No. So if it's not holding together because of positive-negative association, then that makes it covalent. Now, I do want you to be careful. This is a good way of understanding the difference between ionic and covalent, but that being said, how many times have you seen sodium chloride drawn with positives and minuses in it? Not very often. So an ionic compound frequently will not have that positive or minus drawn in it, especially when you're talking about other places in the book. But when we're talking about different types of bonds, we draw them there so that you can appreciate this is an ionic interaction, as opposed to a covalent. Now we will talk about some rules about which things tend to be ionic bonds, which things tend to be covalent bonds. I just don't want you to get confused if you look at sodium chloride on a salt shaker and go, they're writing this wrong, because there's no pluses and minuses here, right? All right. Chemical bonds, covalent bonds, and ionic bonds are formed when atoms lose, gains, or share. I want you to do yourself a favor and put quotes around valence electrons. Mostly what we're going to be talking about, it is true that we are forming covalent bonds because we are gaining, losing, or sharing valence electrons. But if you go beyond the boundaries of what we're going to spend a lot of time talking about, and we'll spend a little bit of time in Chapter 6, but beyond the boundaries of this class, it is not always sharing valence electrons. Or you could say, well, that's not technically true because under certain conditions it forces a subshell electron to become a valence electron, and that's splitting hairs. But for our considerations, for everything that we're going to be working with in here, it's a valence electron that is being shared. And the whole point is to get to an octet. The whole point is to get to 8 in your outer shell. Unless, of course, you're talking about hydrogen or helium, in which case their outer shell only holds 2, right? Because that first shelf in our metaphor of shelves from Chapter 4 only held 2 books, right? If we're following that metaphor, how would you rephrase this sentence in order to make it fit that metaphor? We're trying to gain or share valence electrons to acquire what? A full top shelf, right? To make sure that that top shelf has 8 books or 8 electrons. Now that either means filling up a shelf that's almost full or emptying a shelf that's almost empty, right? The point is we want the highest occupied shelf to be full. Ionic bonds occur, as I said before, usually between atoms of a metal and non-metal. There's your first clue if you're looking at an ionic compound versus a covalent compound. Are you looking at a metal and non-metal together? Well then that's probably ionic, because metals like to lose electrons and ionic compounds like to gain electrons, or excuse me, non-metals like to gain electrons, and so there's your first clue that this might be ionic. If you're looking at a lot of intermediate or a lot of, say, carbon, nitrogen, hydrogen type stuff, then you're probably talking about covalent. If you're talking about nonmetals with nonmetals, those are probably covalent bonds. So here we have the example. Here we have a metal and a nonmetal. The metal, abbreviated M, that's not actually supposed to be a chemical symbol. We're not talking about mercurium or something. There isn't actually an M by itself on the periodic table, just like there's an NM. But metal, M stands for metal, NM stands for nonmetal here, right? So our metal with 1 electron, it's going to give or have stolen, depending upon how you look at it, its electron to the nonmetal, which is going to fill up the nonmetal's shell, right? And it will also leave the metal shell, that top one now empty, which means the one below it is full. How do I know the one below it is full? Because when we were talking about filling up the shelves, did we ever add an electron to a shelf up before we filled the shelf we were on? No. At least not as far as we got, not as deep as we got. You always fill up the shelf you're on before you move to the next one. Now, that is not true if you keep going deeper into the periodic table, but for our purposes, it is. So, here we have, thank you, here we have the ionic association. That metal lost an ion, an electron, so it becomes positively charged. The non-metal gained an electron, so it becomes negatively charged. And now these two guys stick together not because they are sharing electrons, but because they are positively and negatively charged, and those two different attractions, those two different charges attract each other, right? What's the difference here between our two nonmetals? Both of these nonmetals have 7 valence electrons. How do I know? I counted the dots, right? So, what's it going to take to fill up their outer shell? Each one of them needs 1 more, right? Now, if there was a metal around, they could just steal one and be good, and become an ion. But what they could also do is play nice with someone else that also would like to share an electron. And so one of them says, I'll share my electron with you if you share your electron with me. And if they both of them share, then that means both of them get to have a completely full octet, right? If you count how many dots are around each one of them as a center, how many do you see? 8 for each. 2 of them are shared, but there's still 8 for each, right? Positive ions form when things lose electrons. So, your metals, especially in group 1, 2, and 3A. So that's your lithiums, your sodiums, your magnesiums, your calciums, your aluminums from 3A. The metals tend to readily lose 1 or more. Why or more? What would the ionic charge of magnesium be? Magnesium is in group 2. So how many electrons does it have to lose before its outer shell is empty / lower next shell down is full? 2. So that means that it will readily lose both of those electrons in order to form ions with a positive charge. They will keep losing electrons until they have the same number of valence electrons as the nearest noble gas. In other words, they're going to drop down. Magnesium will lose 2 to be the same as neon. It's going to try and lose those extra books off that top shelf, so the one beneath it is full, right? Metals will lose electrons. By the way, anybody remember the name that we would give, not that we're going to spend time doing that math here, but the name that we would give to the amount of energy that it takes to rip off that first electron? Talked about 2 days ago, guys. What are we making when we remove electrons? We're making ions. So it's the energy of ionization. Does that ring a bell? Yeah. Maybe? It's different for different atoms, right? And that's going to be based on how far away. Remember when we talked about those trends on the periodic table? What happens to the energy of ionization as we go down from lithium to sodium to potassium to rubidium? What happens to the energy of ionization? It goes down. It gets easier to remove electrons because the electron is further away from that positive charge, right? What happens to the energy of ionization as we go right through the group? We're getting more and more positive charges in the same distance, so that the size gets tighter, which means they're closer, which means the energy of ionization is going to go up, right? So, a little review from last chapter that we talked about, right? So here we have our sodium atom that is losing an electron. What happened to the size of that sodium atom that is represented here in this picture by the amount of blue cloudy space around it? Why did it get smaller?
Lost a shell.
Because it lost one atom and that outer shell is now empty, so we don't count it, right? Which means the size of the atom, the distance between the nucleus and the furthest out electron is now much smaller. Because the furthest out electron is on that lower shell. So we can literally change the size of atoms, not the size of the nucleus, but the overall size of the atom can change via ionization. Because we're adding or subtracting shells, right? In the same way that as we go down the periodic table, down the group, right, the size of the atom gets bigger, right? Because we're adding more and more shells. Each time you go down one more period, it gets one bigger. Go down one more period, it gets one shelf bigger, right? Those nesting dolls, they keep getting bigger and bigger and bigger as you put it inside the next layer, right? Magnesium, as an example that we've already talked about, is a group 2 when it's neutral, so it has 12 protons and 12 electrons. Magnesium wants to lose both of those outer electrons, those 2 electrons in that top shelf, because then that makes it have only 10, but 10 is the 8 from the second shelf and 2 from the first shelf, right? Which means all of its shelves are full, it's nice and happy, but it's also a negatively charged ion now. Excuse me, positively charged ion, because it has 12 positives and 10 negatives. What's that add up to? Positive 2, right? Once again, they want to get down to where their highest bookshelf is full, where their top outer layer of valence electrons has 8. Those are 2 different ways of saying exactly the same thing. Non-metals, on the other hand, out in groups 5, 6, and 7, why not group 8? Why is group 8 not in this list? And you could say, well, it's because they're not non-metals. Okay, we have different names for the things in group 8.
They're noble gases.
They're noble gases. So why are they not listed here as things that like to gain electrons? Because they're already full. Their top shelf is already full, right? They don't need to gain anything. So out here it says that these guys have very high in 5, 6, and 7. So nitrogen, oxygen, and fluorine on that top row that we frequently talk about, right? 5, 6, and 7. Those guys like to gain electrons. Not just one. Well, fluorine and chlorine and bromine and iodine, those guys only need 1, right? But oxygen needs 2, right? And nitrogen, how many does it need? It's in group 5. How far away is that from 8?
3.
3. So it wants to gain 3, right? But it says that these guys have really high ionization energies. I don't want you to get confused by that bullet point. So what does that mean? Tell me what that means. Inversely, it means that our metals have really low ionization energies, right? Why would that be? Because metals want to get rid of that electron, right? Why would it be hard to remove an electron from oxygen?
Because the valence electrons are closer to the nucleus.
The valence electrons are closer to the nucleus because they're all the way on the right. Remember what we talked about? As you move down the periods from the left to the right, what happens to the energy of ionization? It goes up, right? So the energy of ionization is going to be higher because they're on the right side of the periodic table. That is an accurate answer, but now put it in terms of something that's conceptual that makes some sense. That's not just pure chemistry talk. Why would it be hard to remove an electron from fluorine? It's only one away from being full. Why would it want to give up an electron and be even further away from being full? Would giving up one electron make it empty? No. It would have to give up not just one, not just two, not just three, it would have to give up all of them, right? So ripping that first electron off is hard because it's really close to the end, or, more appropriately, because it's on the far right of the period, and therefore the electrons are more closely associated with the nucleus, which makes the ionization energy higher. Whichever of those things makes more sense to you. They're going to gain electrons until their valence shell is full, until their top shelf is full, right? What's going to happen when they gain those electrons? So here we have a chlorine atom. We gain one valence electron. I don't actually like the way this is being drawn because it's not really doing this. So we have 7 electrons in our shell. We gain one more electron and it makes our shell look like it just had the same increase in size. But is it really getting that much bigger? Are we adding another shelf to this? Are we adding another nesting doll? No, we're just filling up the shelf that we already had stuff on, right? We're not going to calculate size of atoms, so it doesn't matter that the art here is not exceptionally realistic. But I did want to point out that minor error in presentation. So that naked chlorine becomes chlorine minus 1, right? Because it gained 1 electron. All right, so the names of common ions. We have cations. Cations are the ones that are positive. Anions are the ones that are negative. I don't really have a good metaphor for this. Like, well, cats are always positive, so that's why cations are positive. Anybody who has a cat knows that that's not true. Cats are usually pretty pissy. So why don't we call cations the negative ones? I don't know. Like anions kind of sounds like anabolic, and anabolic steroids are bad, and that's just too much of a stretch to make it easy to remember, right? So I don't have a good metaphor for this, so cations are positive and anions are negative. I can't help you out with that any further than that. You'll just have to remember that. So what do we have? Lithium, sodium, potassium, nitride, phosphide, oxide, sulfide, fluoride, chloride, bromide, iodide. Why isn't it just iodine? Are we changing the names over here much? Lithium, what do we call lithium when it's not positively charged? Lithium. What do we call oxides when it's not negatively charged? Oxygen. There's a reason that these have this name, because if I have a potassium positively charged thing with a fluoride negatively charged thing, what's the name of that salt? Potassium fluoride. IBE tells you that it's an ionic compound, and it also tells you which thing is negative and which thing is positive. The ides, are negative. We use the group numbers 1A, 2A, or 3A to determine the charge of these ions. Now, could a magnesium atom lose just 1 electron and have a +1 charge? Could it do that? Conceptually, is that something that could happen? Yes. Does that happen in ionic chemistry? No. Especially not at the level that we're discussing in this class. So, what that means is the ions in group 1 will always have a +1 charge. It means the ions in group 2, if it is an ion, it will have a +2 charge. And if you are in group 3, all the way out on the end over here, why is it only listing aluminum? Why isn't it listing gallium or the things below gallium? Well, that's because aluminum is a metal that acts like a straight metal. There are other metals that are very common metals like iron and copper and things like that, manganese, that are not on this list anywhere. Why not? Well, we'll see them in a minute because they're weird. But everybody that we care about in group 1 is on this table. Everybody we care about in group 2 is on this table. That makes them easy. That makes them straightforward. Nitrogen, oxygen, phosphorus, potassium, sulfur, chlorine, selenium, bromium, and iodine. Arsenic is not on this list. I don't know what Te is off the top of my head. Can you tell that I also did not go through chemistry with teachers that required me to memorize the periodic table? And if I did, it was so long ago, I would have intentionally forgotten.
What about beryllium? Or the B?
Boron?
No, the BE.
In what group?
Two.
Oh, all the way at the top, you're right, it's not there. Okay, I stand corrected. We'll see if it actually shows up on the second table. Because I don't, yeah, that one might be a poly as well. These guys here are singles. They only show up in one ionic form. Which begs the question, what about the other ones? What does that imply the other ones can do? Multiple forms. Alright, so here's some important ions that are especially significant for biology. Sodium, potassium, calcium, and magnesium. Sodium is the principal cation outside of the cell. Potassium is the principal cation inside the cell. You spend, I'm going to go out on a limb here and say, if not the majority, you spend a massive amount of energy, of the ATP that your cells get from your food, from burning your food, a massive amount of that energy is spent on pumping sodium out of the cell and pumping potassium into the cell. So much so that there are millimolar concentration differences between either side of the membrane. Why would you do this? We've talked about it before when we were looking at a picture of a dam. What can you do when there's a really big height difference between the top of a dam and the bottom of a dam?
Potential energy.
You get a lot of potential energy out of that, right? If you harness it right. Well, that's what your cell is doing when it's pumping those sodium and potassium ions. It is using your cell membrane like the wall of a dam and creating a huge difference between the outside and the inside. So that if it opens up a little bit of a spill gate, it can harness all of the energy. But you say, that's nothing like a dam, how does that work? Yes, you're right, but the potential energy of a chemical gradient is just as real as the potential energy of a ball falling or as water falling from the top of the dam to a bottom. It's a real thing. We're not going to do that calculation yet, if at all, but it's a real thing. It's just as real as gravity.
One of the techniques vets use not to get kicked by a horse is they'll hit the skin so they completely deplete any potential energy in the nerve cells, and then give the injection because there's a recharge time.
Right.
If they can get it in there quick.
So effectively, if you make all of the pain receptors fire fast enough, you have a very short amount of time where the next poke is not going to register as a real bad poke. I can believe that because you're right. There is a recovery period of neurons Because remember, I mentioned earlier, a neuron only has two ways of being, right? It's either not saying something or it's saying, hey. Takes a little while to reset that hey button. Regulation and control of body fluids. We get it from salts, cheese, bananas, potatoes, orange juice, all sorts of fun stuff. Can you die from drinking too much water?
Yes.
Yes.
Yes. Why? Has nothing to do with drowning. It's not because water starts to leak in your lungs, so there's no other place to go.
Because osmosis causes an imbalance. Everything.
Yes, specifically, the thing that kills you is the imbalance of this. If you dilute the fluid outside of your cells too much, then those batteries that your cells have spent all of that energy trying to maintain, if they can't actually tap that, if they can't plug into that energy anymore, it causes everything to go foobar at a cellular level. Just from drinking too much water. Too fast. You can drink enough water to kill you, but if you spread it out over a long enough period of time so that your kidneys and your sweat glands can get rid of it, then you'll be fine. Because over the course of a year, you drink more than enough water to kill you. The difference is, you drank it over a year. It's a colloquial story, but there's like, the one that I like to use is, I remember hearing a radio story, maybe a little less than a decade ago, a radio station that ran a competition of how much can you drink, don't pee for a wee. They were like, the one who drank the most was going to win a Wii gaming system, and the winner was awarded the prize posthumously because she died. But at least her family got to enjoy a Wii. Sure, it was totally worth it. Calcium, cation that you find outside the cell and in the bones, we use this for muscle contractions. Calcium flooding into your muscle cells in response to a nerve impulse is the thing that makes your muscles contract. Because it's the thing that activates the fibers, the tiny little proteins in your muscle cells. They are always wanting to pull. Because that's what muscles do. They always pull, never push. They are always wanting to pull, but the problem is most of the time they can't because they don't have any calcium. And if you don't have calcium, then they can't bridge the connection between the two different fibers that want to pull. Question?
So how are extensor muscles working?
You have muscles that can help extend something, but that's still pulling on the backside of a joint, if that's what you're talking about physiologically. Muscles never push. They always pull. That's the way muscles work. At least to my understanding of physiology. You can find something that I'm completely unaware of.
No, it's making sense now.
Right, just like every set of muscles that you have of skeletal muscle always comes in a pair. Your bicep that pulls your arm closed. How do you get that arm straight again? The tricep pulls on the opposite side of the bone. Muscles always pull. So even the thing of act of straightening your arm is still a muscle that's pulling on the back of that bone. All of that requires calcium. Not enough calcium, muscles don't work well. Magnesium, another cation found outside the cell, also is involved in muscle contraction and frequently involved in cramps. When you have poor magnesium distribution. Alright, so let's talk about some ionic compounds. They're going to go here. We need to be able to write the charge balance, which we should already be able to do because we've talked about that, right? And write the correct formula for an ionic compound. What's the formula for sodium and chloride? Well, they're both +1 charges, right? So the formula is sodium chloride. +1, -1. The whole point is when we add that +1 and that -1 together, what do you get?
Happiness.
Happiness of 0. Ionic atoms will form ionic compounds that are no longer ionic. An ionic compound should have a charge of 0.
Would it be wrong, metaphorically, to think of it as symbiotic?
As a metaphor, that might sort of work. I mean, I don't know what benefit they're getting out of it because they're not happier when they're around other charges. They're certainly happier than they would be if they weren't around other negatives. So the other charges protect them from the negative charges or vice versa, sure. Now I should point out the thing that I just told you, ionic compounds are always going to be 0. You can put air quotes around that if you'd like, because we're going to talk about ions that are made up of multiple atoms that still have a charge. You guys heard of sulfate, phosphate? Heard of these things? Nitrates? These are multiple atoms put together that still have a charge, but we very rarely find them floating around in their ionic form because they're used in making ionic compounds where the total compound has 0. Positive, negative ions, they are attracted because of the ionic bonding between those two things. They tend to have high melting points. Why? Because ionic bonds are strong. What's melting mean? It means going from a solid to a liquid, right? In order for something to be a liquid, individual atoms have to be able to move around each other constantly and fluidly. And ionic things don't like doing that because, well, there's those positive charges over there, negative charges over there. We don't like to hang out with one of those. We really like to hang out with the other one. So there's high melting points because it takes a lot of energy to loosen those bonds enough that they'll start sliding around. So if they have high melting points, room temperature is not considered a high temperature, right? So if your melting point is very high, what state will you be in at room temperature? Solid. Sodium chloride, table salt. If you magnify crystals, it'll actually be able to show you that there is a crystalline organization, there's a lattice structure. If you get down close enough, you can actually see that as it's drawn here, with our sodium and chlorine ions, intercharge or arranged, what do you notice about that? If we could zoom in on it a little bit more, you would see that every sodium, those tiny little purple dots, they are surrounded by negatively charged chlorine atoms. Why wouldn't they have other sodium atoms anywhere near them? Because positive charge repels positive charge, right? Because just like before, as each one of those sodium is surrounded by chlorine, each one of those chlorines is what? Surrounded by sodium. When we talk about covalent atoms later, you're going to have an individual chemical formula, and there will always be an exact ratio for that chemical formula. What's the ratio of sodium to chlorine here? It's pretty much 1 for 1, but it's not divisible. We can't pull one of those things out because that one sodium doesn't belong to the chlorine next to it. It belongs to all of the chlorines around it. They're all holding on because they all like that ionic interaction just as much as everybody else. So, when we write the chemical formula for these guys, we write them in terms of the lowest whole number ratio of atoms or ions that we can in order to make the charge equal to 0. Because complete ionic compounds are going to have a charge of 0. Once again, with that little asterisk next to it, that there's some other guys that make this messy. And we'll talk about them in a minute. So sodium chloride becomes sodium positive charge 1, chloride becomes negative charge 1. So we write this as sodium chloride because we don't need just a 1-to-1 ratio is good, right? Sodium, same name as before, right? But chlorine is not chlorine anymore, it's chloride, which tells you that this is an ionic compound. So manganese chloride, or magnesium chloride, excuse me. Magnesium has 2 electrons that it likes to lose, so it will give 1 to each of the 2 chlorines because chlorine will only take 1. Why would it not want to take 2? If it likes 1 electron, why wouldn't it like 2 electrons? Right, because only 1 gives it a full shelf. If it takes 1 more, what's it doing? We're adding 1 more to another shelf now. That defeats the purpose, right? So in order for that magnesium to lose both of its electrons, it has to find 2 chlorine atoms to give it to. So we have a +2 for the magnesium. Chlorine's only -1, so how many chlorines do we need? We need 2 of them. So what's the whole number, smallest whole number ratio of these 2 atoms? magnesium 2 chloride, or MgCl2, right? You wouldn't put magnesium 2 chloride like this. Why? Because people might get confused and think that that 2 is right here, right? Which we're going to talk about that for test prep later, just in case we have to. But that's only if we get through all the way through this chapter. Because this chapter is a pain in my butt when it comes to putting these questions online. Because transferring these questions into D2L does not allow for fonts, which means subscripts and superscripts don't transfer. Which means I have to type all these things in manually in D2L, and that's a pain in my butt. But, you know, I'm a dedicated teacher and stuff, so do it!
They won't let you use an illustration?
If I want to upload them all and link to them, which would take even longer than just adding it manually and telling. Because in D2L I can tell it's a superscript subscript, but after I write it in, so like every individual 2 and 3 and whatever has to be superscripted and subscripted in every question. I hate it. But this is a chemistry course, so this is like, oh, this is gonna suck.
Can't you copy and paste them from another program? So
You-
set it up in Word or whatever?
See, you'd think so, yeah, but not for D2L. For D2L, it can only import it as a comma-separated limited file, which means it has to be straight text, which means you can't use superscript subscript. If I could get it imported into Blackboard, which could do a better job of it, and then that exported as a unit, which could then be imported into, but I can't do that because we don't have the thing that makes the Blackboard thing that makes the. These are my crosses to bear, not your crosses. So,
Can your CBL file include markup?
CSV, comma separated file. So no, it can't. It's just straight ASCII text.
Well, I mean, markup is ASCII text.
You mean the HTML markup? What are you talking about? No, I tried it.
Okay.
And plus, typing it all into HTML doesn't really save me time either.
Well, you can paste formatted text into something like Word. And
Oh, and then
export
have
that.
it displayed as HTML. That's true. But no, I tried it. It doesn't work. Not in the import.
Got to just.
So, here we have sodium and a sulfur atom. So sulfur wants how many electrons? It's in period 6. That is how many shy of 8?
2.
Just take group 6, not period 6. 2. So it needs to get 2 electrons. Sodium can only give 1 each. Why can't it give 2? Well, technically it could, but it's only got 1 in its valence electron, right? And so if it gave 1 more away, then that top shelf wouldn't be full anymore, and that defeats the purpose. So it'll only give 1 away. So now we have sodium has 1 positive charge, sulfur has 2. So how many sodium atoms do we need? 2 of them, right? So this is Na2S. Sodium sulfide. Question?
Oh, when is it sulfate?
We will get to that. Sulfate, sulfite, hyperchlorite, hypersulfite. Yeah. Fun stuff! And those are the things where ionic compounds that don't have a 0 charge, but that's why they are a compound that is part of a compound. Right? So we'll get to them, I hope, eventually. So how do we name this? Morton salt. That's not how you name it, that's just a brand.
What?
What's that?
Nothing.
Okay. So when we name an ionic compound, we write the metal first, and it's just the same name as an element. We've already seen this, right? We talked about it before. Sodium is not sodium chlorine, it's sodium chloride, right? But we use the metal name is the same, and then the non-metal gets the same first syllable, chloride, fluoride, bromide, iodide. We use the first syllable of the non-metal and then add the ide. That tells you it's an ionic compound. This is how we name things. This is also why you'll note that we have not had any dis or tris or tetras, right? What do we call this guy all the way back here? There's 2 sodiums and 1 sulfur. Why isn't this disodium sulfide? Well, because if it's an ionic compound, we don't need that. It's just sodium sulfide. Because sodium has a charge of +1, sulfide has a charge of -2, so that tells you how much of each one you need, right? Question?
Just like, is I always going to be an ionic ending in this type, or no?
I'm going to say yes.
Okay.
Trying to think of other. Yeah. I'm going to say yes. Until we see something that says otherwise. Put a space between the names of the metal and the non-metal. Potassium iodide, magnesium bromide, aluminum oxide. It doesn't matter what the numbers are here because it's an ionic compound. And so we don't need tetras or dyes or any of that. It's just the metal and the non-metal. Because potassium iodide is easy, right? +1, -1. So that just means it's a 1-to-1 ratio. But what's aluminum oxide? Aluminum's +3, oxygen or oxide's -2. So what's that going to be? What's the smallest whole number ratio that you can get to make the total pluses and minuses equal 0? 6. So that means we need how many aluminums? 2 of them. And how many oxides? 3 of them. So Al2O3, but we just call it what? Aluminum oxide, because it's an ionic compound. Everybody follow? Name this ionic compound. Potassium oxide. The metal is the same. Oxygen minus Gen plus I. Oxide, right? Potassium oxide. How much would it take to do both? Well, oxide has a -2 charge, so we need 2 potassiums, right? So that's where that K2O comes from right there, but we still just call it potassium oxide. Everybody follow? We're good on that one? Here's some example for naming. What would that be? Calcium oxide, that's what? Aluminum sulfide, that's magnesium chloride. Beautiful. Walking all the way through that. I should have removed these. Why did I not remove these? Did I just miss them? All of this should be in the problem set. I guess I just missed them. Alright, here's the thing. So far, this has been easy. This has been simple. Remember that table where I told you these guys are simple? They only come in one form, right? Beautiful! Alright, now we get the troublemakers. So here are some other metals. Copper, but we get copper 1 or copper 2. Iron, we get iron 2 or iron 3. You can get more than that, but we're not going to talk about it. You can get lead 2 or lead 4. You can get chromium 2 or chromium 3. There is a finite amount of ways in which these things will be comfortable. In the same way that, yes, you can get a magnesium atom and you can force it to lose only 1 electron, but it's not going to stay that way, because that's not stable. But this is iron. Where's iron on our periodic table here? Fe, blip, right there in the middle of our transitional elements. Cobalt, blip, right there. Nickel, right there. Copper, right there. Oh, where's chromium? Chromium back there behind manganese. Our transitional elements. Now remember, what was weird about our transitional elements when we were talking about those shelves? When it was that first shelf only has 2, and the next shelf has 8, and the next shelf has 8, right? What was weird about those transitional elements? We like to say that that 4th shelf only has 8, right? But actually, it has another 10. So that 4th shelf can actually hold 18. And that's why these transitional metals here in the middle, these guys are the troublemakers. Because sometimes a non-valence, something that you would consider to be a non-valence electron, reacts as if it's a valence electron. So that's why iron can lose 2, or it can also lose 3. Now, would we name things the same? Our naming nomenclature is going to be the same thing. So how can you tell the difference between a copper ionic compound that is copper 1 versus copper 2, right? Because if this is, let's say, copper oxide, does that tell you what you have? No, because do we have 2 coppers for every oxygen, or do we just have 1 copper for every oxygen? So what would we need to add to this name so that we can be clear when we're naming our copper oxide which one it is?
Have a different ending.
We could have a different ending, sure, or we could just do exactly what they're showing us here. We could just name the copper. Here's some bismuth. Yep, so that answers your question. Bismuth. Bi? No, your question was about
It's beryllium, isn't
Be.
it?
Yeah, I think it is. I don't know. I
I
have to
know
look it up.
Br is boron.
Right.
So you were talking Be, right?
Or,
It's like,
yeah,
it's
B.
beryllium.
Beryllium.
Yeah,
I don't see it on here.
because I didn't.
I don't know why it wouldn't make ionic compounds.
Can you
So-
do it with beryllium though?
Can you what?
Like, if it was a question, can you do it with beryllium?
I don't see why not. I mean, there might be something special about it that makes it so uncommon as to be not worth talking about in an introductory textbook. But conceptually, yeah, it can make an ionic compound with whatever it is that fills it up. If it only makes 1 ion, or if it makes 2.
How do you know if it's 3 or 4 or 2 or 3? Again?
Well, depending on what you're looking at, by the name, or by the formula. So, if, like for example, I could say, in this salt, where it's Fe2PO43, which is iron phosphate. What's the iron? Is this iron 2 or iron 3? Well, to figure that out, you'd have to do the math. How much negative charge do we have here? So how many positive charges do I need on the iron to equal it out, right? Or I just call it iron 3 phosphate. So, there you go. So, when we're making our salts, when we're naming them, these troublemakers, all of these guys right here, this table right here, you can't just call it copper oxide. You can't just call it copper I, right? Whatever the other thing is. It's got to be copper 1 or copper 2. The name is not complete unless you tell us which one it is. And the reason for that is because all of these guys can form either of those ionic states relatively easily. So we have to know. It's not like one of these things only occurs once in every 10 million molecules. So this is a nice table. When we get to things like tests, where you might need to look something up that's useful for certain portions of chapters of questions, being able to know where things like this, where we have a high amount of information in a concentrated area, might save you some time. Just saying. We've had a few other tables that are like that too, right? Tables with a collection of conversions that might save you some time if you could quickly find that table. Because I don't expect you to memorize all of this stuff, but I do expect you to be able to find it and answer questions about it. Okay? Make sure. Mercury 1 ions form an ion pair with a +2 charge. Okay, sure. Mercury 1, but it's listed as Hg2 2+. So you're only going to find mercury 1 ions if there's 2 of them together. So in other words, you're never going to find mercury 1 chloride. Because mercury 1 is not stable unless it comes in pairs. So you could have mercury 1 oxide, but that would be Hg2O, right? Mercury 2 is stable by itself. This might be one of the reasons why it might not ionize from it. Like, there's something weird about it being in a location it might not like to do this, in the same way that Mercury doesn't like to be a single ion, unless there's pairs. I'm gonna have to look that up, because I have no idea why it's not even on there anyway.
Yeah, because it's not even listed on the next
Yeah,
thing. Sorry.
I mean, yeah, this is, I don't know.
It's not.
It is not something we need to worry about, evidently. That doesn't make me feel any better, like, that just makes me why. All right. Variable charge. So here we have MnF2. If you were going to name that, what would you call it? Our fluorine has a -1 charge each, right? So our total negative charges is -2. So which version of manganese is this? It'd have to be a +2 charge, right? So the name of this salt would be what? Manganese 2 fluoride. Make sense? I can guarantee you there will be questions like this on the test. What's the name of this salt? Here's a salt, what's it made out of? That type of stuff, right? Go back and forth between having the chemical formula and giving the name. I give you the name, you give me the chemical formula. Guarantee you it's on there. How do I know? Because I just spent a whole bunch of time writing all this stuff into D2L, right? So it's like, all right, there we go. Because I'm the teacher. I know all the questions. No, I don't.
Also, it's food.
I have checked all the questions, but that doesn't mean that I remember them all. Oh, I should point out, actually, while I'm on the subject, this is the first time I'm teaching this course, it's the first time I'm using this book, it's the first time I'm using these questions. I am human, and so are all of the people that did all of the work that I didn't do before me. So if you feel like you got a question wrong on the exam, and you look it up, and like, no, I checked, and I still think I should have got this right, talk to me about it, because it's entirely possible that I'm burning through all these questions and I didn't notice that that one was scored wrong, or maybe I typed it in wrong or something. So if you're right, I'll give you credit. That does not mean that I want to know, like, I had one student one year that just wrote me an email and said, could you please explain why I got everything wrong on the test? The answer to that email was really easy. No. So don't do that. Look it up. Because a lot of them like, oh, I see what I did there. All right. But if there's one where you're like, no, wait, I looked at it. I still think this is right. Then, yeah, email me about it. Come talk to me about it. If you're right, I'll give you credit. Plus, you're not just helping your grade, you're helping everyone else who takes this class after you, because then they get to fix that question so that they don't get confused by it. You're not technically helping everyone else who's taking the test with you, because if they didn't notice, if they weren't motivated enough to check and notice, then I guess they're just okay with living with a bad grade. That, because it's really a pain in the butt to change everybody's grade question by question. Because you might have been the only one who got that question this year, right? So, seriously, there's like 60 to 70 questions per chapter. All right, so, ionic charges. Once again, here is a slide that has a lot of information densely packed, right? Maybe an even better slide than that last one, because this has all of our individuals and all of our doubles and triples, right? So this might be a good slide to have, like, easily accessible. Or maybe just like a little sticky note in your book, or what page that's on or something like that, so you can flip to it quick. This is me trying to give you a few tips and hints, because I do know that 50 questions where a significant number of them are math questions, it's going to take you some time to do that. I'm hoping 2 hours is more than enough, but I'm not 100% sure.
Just acting.
Yeah, 3 days. It needs to be long enough that you can look up stuff that you're not sure, but short enough that you can't just look up every single question. I know. There's a sweet spot in there somewhere. I'm not sure where it is.
3.5 hours?
2. And I will say this, if everybody does poorly and nobody finishes in 2 hours, then I will adjust, right? Like I said before, I'm not here to force bad grades on you. So don't sweat it, but you know, if I find out that there's some sort of like suicide pact of everybody only answering half the questions in 2 hours, then that's no. Yeah, I'm not here to browbeat you guys. I'm here to teach you chemistry. So
If you find that out, isn't it too late?
Right.
no, if I find that out, actually that would be considered cheating, and then we'd be talking about
No,
academic
suicide
honesty. Was that?
Suicide pact.
Oh. Okay, I meant that as a metaphor. Not as literal suicide. Naming ionic compounds, we've already done this, right? Here we have FeCl2. Chlorine has what charge? Positive, or -1 each, right? -1 each, because chlorine likes to add an extra electron. So what's that iron got to be? -1 for every chlorine. There's 2 chlorines, that gives us a negative charge of 2. Which means our iron has to be a positive charge of 2. Which means this is iron 2 chloride, right?
Oh, I get it.
As long as that confusion dissipates, that's fine. Whatever works. So, this is just going backwards. This is what I just told you you would need to do, right? This slide and others. So if I give you a name, you can give me the compound, right? If I give you a compound, you can give me the name, right?
We could try.
Yeah, sure. I mean, makes sense now. I don't know how I'll feel about it on Saturday when I haven't thought about this for 48 hours, but you know, I know how it is. Well, this page doesn't actually tell you much, but here we go for some examples. Write the formula for tin 2 chloride. Let's try it. I think tin is SN. Yeah. So tin comes in either a 2 or a 4. That should make this easy, because those are your only options, right? So, write the formula for tin 2 chloride. What is it? SnCl2, right. Because tin 2 means it has a positive 2 charge, right? And chlorine has a +1 charge, -1 charge each. So we need 2 of those, 1 tin, 2 chlorines, so tin 2 chloride is SnCl2. SnCl2. See, we got this. You got this, right?
Can you go back to the table?
Yeah?
Why is this not related to sulfide? Why is it related?
Okay, that's a good question. It says lead 4 sulfide.
Yeah.
All right, so let's work out lead 4 sulfide. So, what's sulfur? What does it want? As an ion, it is what charge? It starts in group 6, so how far away from 8 is that? 2. So that means that every sulfur atom is going to give a -2 charge. So if we have 2 sulfur atoms, what would the total negative charge be? -4. So in that particular case, 1 lead, 2 sulfur. What if the 2 sulfurs are 2 each? That gives you a -4 charge. What's the lead got to be? It's got to be +4, right?
Yeah.
And if we look back, let's double check our table. Sorry for paging through this. Is lead 4 an option? Yes, it is. So we're good. That's a good thing to check, by the way. If you do it, you're like, that's lead 3. Double check, because if that's not an option, you did something wrong.
So it seems like the reason there's so many slides in here is because I've left a lot of these working, well, I went too far. A lot of these work through stuff still in there. Which isn't bad. I mean, I should point out, there are practice problem PowerPoint sets. If you are confused or want a little extra practice, load up those PowerPoints and look through them. And it walks you through this stuff just like this does. Don't just read it all, try and do it, and then check the next step. Question?
The one for the math. There's one for the math.
There's one for every chapter. Yeah. So, and they should all be there. So there's chapter X notes, and then there's chapter X. I evidently didn't keep my nomenclature the same, so it's either chapter X practice problems or just chapter X problems. Right. They are PowerPoint slides that are extra examples like this, where they say, how would you do this? And then the next few slides work you through step by step. So if you just read them, then that probably does nothing for you. But if you say, how would you do that? All right, well, let me try. And then look at the next slide and be like, well, am I doing everything right? And look at the final slide. Hey, I got it right, yay! And if you got it wrong, you can be like, what did I f up? And look at it, and maybe learn, not do that again, right? Question?
Okay, so with that like practice problem thing, is there a way where you can kind of correlate to like the section of like the book of the question that you're asking? Like sometimes I look at it and I'm just like, where did this come from?
Okay, so here, I'll tell you how I do this. I took the slides from the publisher. And this is what I was complaining about a moment ago, is I manually remove the practice problems that are listed as learning checks. Because those are quite specifically extra problems to double check and see if you've figured this out, right? It's like, did you get it? We just talked about this. Did you get it? They already have some questions like this in the slides already that I do leave. But the extra ones that would require us to be here for 6 hours for me to go through them all on a day, chapter by a day speed, right? I pull those out and put them to the side in their own PowerPoint. So they're going to go through, I don't like randomize the slides. So it's going to be in order, roughly section by section, but it does not mean here's a practice thing from section 2.1 and here's a practice thing from section 2.3. But if you go through it and read, when you get to a part where you're like, I don't remember how to do this, go back to that chapter, find out which section that is, and reread it. Right? But if you go through that whole thing and you're like, I got this, I'm good at all these, then that means that most of the major concepts you've got pretty well down. So if you can work through the practice problems without an issue, that doesn't mean you don't need to study, it just means that you're studying fairly well. Got it? No? Don't got it? Still believe it?
Don't believe it.
There we go. Okay. Alright, so let's talk about polyatomic ions. Polyatomic ions. These are the other problem right here, the sulfites, the sulfates. Alright? Polyatomic, which means they are technically a compound, because that's what a compound is, right? Multiple atoms of different types. But they are also still ionic. So polyatomic ions. Aluminum hydroxide. So we have put the hydroxide here in parentheses because that is the ion. It is a polyatomic ion. What is the charge of that hydroxyl ion? Be a bit more specific. Yes, 1, but which one? Positive 1 or negative 1? Negative 1. Because the aluminum is going to be positive 3, right? It's in group 3, but it's a metal, so it wants to give up 3. So we have 3 of them right there. It told us that. So that means that each one of those hydroxyl polyatomic ions has a net charge of -1. Where do you find a lot of these hydroxyl ions? Yes, actually in medications. Once again, because a lot of medications are salts. They are ionic compounds. But the place where you find a lot of these hydroxyl ions is water. Acids, bases. An aqueous solution with a whole bunch of hydroxyl ions just floating about is a very basic solution. as opposed to one that has a whole bunch of hydrogen ions floating about, is a very acidic solution. We'll talk about that later.
Do we have to?
Unfortunately, or fortunately, yes, we do. Because pH is really important in biological systems. And when we get to those chapters, we'll talk about why. And if this book doesn't cover it in enough detail, I will rant about it a little bit more.
So possible.
Would that be aluminum 3?
It would be, except that aluminum only has one way to be. So it wouldn't be aluminum 3, it would just be aluminum. That's why we learned about how to name the easy ones first. The only time that you have to add the 1 or the 2 or the 3 or the 4 is if there's more than one way to be. Like these transitional elements in here, right? Aluminum only has one way to be, so it's just aluminum hydroxide.
Yeah, it shows it on here that it's... I got it, never mind.
Perfect. Polyatomic ions, a group of atoms that still has an overall charge. The most common ones that we're going to talk about is a non-metal like phosphorus, sulfur, carbon, or nitrogen that's covalently bonded with oxygen atoms, because oxygen is weird in so many ways. Oxygen is weird, and so we can have these polyatomic atoms where oxygen is just being really what's the word for sleeps around a lot?
Promiscuous.
There we go. The non-slut-shaming word for sleeps around a lot. Oxygen's just really promiscuous. Oxygen likes to make lots of friends and doesn't care. It's like, what more the merrier. It's like, can I bring my friend too? Sure! Oxygen's weird. We wouldn't be here without it, and if it was just a little bit different chemically, we wouldn't be here with it. That may not make sense to you, but that's one of those things I can tell you about like way later in this term and after class. Get me ranting about it and it'll be fun. It'll be fun for me. You're free to leave. I'm gonna start doing that if you want, like after class, whatever. That's optional. So anyway, they have a charge of -1, -2, or -3. We have the negative charge. All of them are negative except for one, which also is not being promiscuous with oxygen. It's ammonium, which is NH4 positive. That's the only positive one that we're going to be dealing with.
And it cannot do anything with oxygen?
No, it can.
Okay.
It's just that that particular all the ones that are being promiscuous with oxygen are negative. But the ammonium ion is a positive polyatomic ion. It's the only one that we're going to care about. It might be the only one realistically, period, but it's the only one that really matters in biological systems, in organic chemistry. Because if you get into inorganic chemistry, things get really weird, but we're not going to worry about that. So, here we have calcium, and here we have a sulfate ion. SO4. Now, if you're wondering, because you should be wondering, how do you take a sulfur and 4 oxygens and put them together and it only has a net charge of -2? That's a good question. And it's because these guys are covalently bound to each other in a weird way that has a lot to do with dispersed electron cloud density and stuff that we don't have time to get into. But it's a polyatomic ion. This here is a covalent molecule. Everything we've been talking about so far is forming ionic molecules, right? Ionic bonds. But that sulfate ion is a covalently bonded molecule. That oxygen is not hanging out with that sulfur because of positive negative charges. It's hanging out with that sulfur because it is, let's say, permanently with air quotes, because anything in chemistry can change with enough energy, right? But it is covalently bonded to that sulfur. And the overall charge of that polyatomic molecule is still -2, which makes it a polyatomic ion, because it has a net charge.
Okay, so anything with like the oxygen and sulfate is 8.
Yes, one example of them. Hold that thought. Because so here's sulfate, here's nitrate, right? So the question that you have is, so here we have our nitrate, here we have our chlorates, here we have our carbonates, right? Here we have our sulfates and phosphates. And yet we could also get nitrite or chlorite or hyperchlorite or perchlorite. All of these are chlorine with oxygen. So you see why I talk about pervasiveness? Here we have a chlorine that's just being monogamous with this one oxygen friend. Here we have a chlorine that's having a little threesome. Here we have a chlorine that's just going crazy. It's one chlorine and 3 oxygens, and that's not even the end of it. Sometimes you can get one chlorine with 4. What do you notice about the charge here? It's always what?
Negative.
Negative 1. That is not always true. Now here we have, well, let's be fair. Here we have sulfate. It is a polyatomic ion. It is SO4. It has a net charge of -2. When you add it together with one hydrogen, you get hydrogen sulfate. But the net charge is now only -1. Why? Because that hydrogen is bringing a positive charge with it, so the -2 plus 1 becomes -1, right? But it's still SO4, so it's still sulfate. So, here's something that should confuse you, but hopefully we can get this cleared up. So nitrate up here, that's NO3. Chlorate is chlorine O3. Carbonate is carbon O3. Noticing a pattern? Sulfate is sulfur O4. Crap. Well, we were on a roll there for a while. So 8 does not always mean 3. The 8 is actually a term that we use to recognize the most common polyatomic ion combination that we will find. So the most common carbon polyatomic ion is carbonate, and that's CO3. The most common sulfur polyatomic ion is SO4. The most common chlorine ion is chlorine O3. We call those 8s, chlorates, sulfates, phosphate, PO4. So this is another one of those things where you're just going to have to either know where to find the table, or you're going to have to remember what's the most common form. And that's the 8. You ate the most common one, because that's the one that's easiest to find. So what are the other things? What's the difference between nitrate and nitrite? 1 less oxygen. What's the difference between chlorate and chlorite? 1 less oxygen. But can we go even lower? Sure. What's the difference between chlorite and hypochlorite? 1 less oxygen still, right? So hypo means less. So chlorate is ClO3, chlorite is ClO2, even less than ClO2 would be ClO1, right, or just ClO, and that's hypochlorite. And what would be one more than chlorate? ClO4. Perchlorate or hyper, right, hyper meaning more. So these polyatomic ions, the naming for them is, it makes sense when you're like just walking up or down, right? But where you start from, that's something you either just have to know or have to know where to look at. Everybody follow? Question? Maybe a question?
No.
Unsure of a question?
I was thinking like if I found a pattern with like 8 and I did not.
Yeah. Now, you can just say 8 is 4 for S and P, and 8 is 3 for C and C, maybe? C and Cl, I guess.
So S and P.
S and P, sulfate is SO4, PO4, right? So S and P is 4. And C and Cl is 3 for 8s. And nitrogen is just weird. Nitrate is also 3, so I guess you could say 8 is for C, Cl, and N. But I mean, it's at some point you just got to know it, right? Like, or know where to look it up. One of the two. Okay.
But then hydrogen.
Hydrogen by itself is just an ion. Hydride or hydroxyl, excuse me, is always just OH minus.
So would you say it's always negative with hydroxide?
Hydroxide is always negative, yes.
Okay.
As an ion, yes, it's always negative. Out of curiosity, little quick trick. So carbonate versus hydrogen carbonate, the -2 comes down to -1, right? Because we added an H to it. What would happen if you added an H to that hydroxide? What would you get? Right, if we added an H to that hydroxide, just like if we added an H to the carbonate, it becomes hydrogen carbonate. The charge goes down by 1. It'd be 0 neutral, but what would we call that molecule?
Which one were you pointing at?
This one up here. If we added an H to hydroxide. Don't. This is a kindergarten question. Water. We would call it water.
H2O.
Oh my god.
HOH, H2O.
That was.
There we go.
Fast.
See? Water will frequently just split. So H2O will frequently split into OH negative and H positive. Because hydrogen is just one little proton with one little electron, and it's not very strong. It can't hold on to its electron very well. And oxygen's a big, mean bullet. And so when oxygen shares electrons, frequently it doesn't really share them. And so that